It's a pleasure. Welcome, everyone, and a pleasure to introduce Escher Searle from Wichita State University. We'll speak on almost isotropy-maximal manifolds of non-negative curvature.
Thank you. Thank you for the invitation to speak too. So it's a pleasure to see you guys. Hopefully in person at some point, right? So yeah, I'm gonna be talking about almost isotropy-maximal manifolds of non-negative curvature. This is joint work with Zhiqing Dong and Christine Escher. So I just want to start off and say, actually, I'm gonna make sure I don't have the huge eraser on here. So I just want to recall that if we're looking at manifolds that are closed, simply connected, and of positive sectional curvature, if we're looking in dimensions bigger than 24, the only known examples we have are spherical in nature. So they're going to be spheres or quotients of spheres. So complex projective space and quaternionic projective space included. So in contrast, so essentially, you go up to dimensions bigger than 24 and you only see essentially, well, in even dimensions, 0 mod 4, you're going to see 3 examples. 2 mod 4, you see 2 examples, and in odd dimensions, only 1. So in contrast, if we look at non-negative sectional curvature, again, I want closed and simply connected. Then we have vastly more examples. So we got products. I'm just going to name a few. So you got products of non-negatively curved. Let me write that better. Homogeneous spaces with a bi-invariant metric, for example. And in general, metric submersions. So, this is an etc. So despite the fact that we have this huge number of examples of non-negatively curved manifolds, and so few examples, at least in dimensions bigger than 24, and we have a bunch of random examples in lower dimensions, but not that many either on some level. Despite the huge disparity in examples that we can enumerate, we actually have no known obstructions that allow us to distinguish between these two classes. So if I write M and K, or that should be a kappa really, if I can make it, this would be closed, simply connected, curvature bounded below by this kappa. I want them to be n-dimensional too. If that's that class, then we know that obviously if it has positive curvature, it'll be contained in those with non-negative curvature, but we actually don't have any obstructions that allow us to distinguish between these. So, we don't know if that's actually not equal. On the other hand, though, if we assume symmetries, we can distinguish. I'm misspelling symmetries. So maybe I don't know if this is the earliest example of this, but if you go back to the Sheng and Kleiner paper, right? Look at a T1 action on M4, and then if you assume positive sectional curvature, then you only get the 4 sphere and CP2, and if you assume non-negative curvature, you get these 2, of course, but you add in 3 more examples. Okay, so in this talk, though, I'm going to focus on torus actions that are almost isotropy maximal. So and I want them on non-negative, yeah, the same class of manifolds. So this is on non-negatively curved, simply connected, and closed manifolds. Okay, so before I get to that, I want to give a little bit of background because, well, I know Christine knows what almost isotropy maximal means. Maybe the rest don't. So just to start out, so I'm going to say that the torus action, first we start with isotropy maximal. So it's isotropy maximal if we've got a point with an orbit such that the isotropy group is equal to, so this is the dimension of the isotropy group, is equal to the cohomogeneity of the action. So, and that in fact is the largest possible rank we can have for the isotropy subgroup. So this is equivalent to saying then that there exists an X such that the rank of TKX is equal to n minus k. Okay, so for manifolds with positive sectional curvature, it turns out that isotropy maximal torus actions actually correspond to torus actions of maximal symmetry rank, and this follows by the theorems of Berger and Sugahara. So we know that I'm going to start abbreviating isotropy maximal with IM. So it turns out that IM is actually, well, so maybe I should write it this way. M1n of IM is equal to M1n of maximal symmetry rank. So this is, you can use the theorems of Berger and Sugahara to see this. Okay, so on the other hand, if we're looking at non-negative sectional curvature, we actually don't have any analogs of these theorems. So,
sorry, Catherine, what's maybe this is an obvious question. What's maximal symmetry rank?
Okay, so do you know what the symmetry rank is? Or like I should
the rank of the isometry group?
Yep, sim rank of M is going to be equal to the rank of the isometry group of M. And then for positive sectional curvature, Kirsten Grove and myself showed that the sim rank basically is, so what do I want to say here? So yeah, I want to write it this way. If you have TK acting on MN, then you know that K has to be less than or equal to n plus 1 over 2, so roughly half the dimension. And then in the case when K is equal to n plus 1 over 2, that implies that M actually is equivariantly diffeomorphic to the following manifolds with a linear torus action. So it's equivariantly diffeomorphic to a sphere, a complex projective space. I'm omitting its RPN as well, and lens basis. So those manifolds, I mean, basically, if it's isotropy maximal, so what I'm saying here is if you have a torus action that's isotropy maximal, then you just use the fact that any torus action, so in the even dimensional case, if you use Berger, that tells you that you have, if you have a TK action on MN, then you know that the TK has to fix a point. And then you can just, yeah, it's just a simple calculation to see that, well, you can do it from here too. You can see that if T2K minus N is actually equal to 0, or what do I want to say, sorry, 2K minus N is equal to 0, then that gives you that, in the even dimensional case, that gives you this bound. Does that make sense?
Yeah, of course. Thank you.
Yeah, okay. Maybe I gave you way more detail than you really wanted. Sorry.
I think the more the better. So
Okay, okay. I've got plenty. I can give lots of detail. So, so yeah, what I was saying though is that there are no analogs of the theorems of Berger and Sugihara for non-negative sectional curvature. Yeah, I'm going to put it at the beginning of it up at least. So Christine, Escher, and myself, we generalized work Wiemuller. This is like where he classified, well, basically he classified closed, simply connected, isotropy-maximal Tn actions on 2 n-manifolds. And these are also known as torus manifolds. And then, as I was saying, Escher and myself, we obtained the following classification theorem. So we extended his result. So yeah, what did we do? We take a torus. Now we did it for all ranks basically that are possible. So this is the lowest possible rank that can occur, so you're going to see. And we showed that you can extend that. You can get isotropy-maximal actions from for K within these bounds. So bounded below by n+1/2 and above by approximately 2/3 the dimension. And that in all those cases that we know that the manifold is then equivariantly diffeomorphic to this quotient, where this TL is acting freely and linearly. And it's equivariantly diffeomorphic with respect to a linear TK action on this guy, where this is a product of spheres. So you've got even dimensional and odd dimensional spheres. The odd dimensional spheres have to start out at least being dimension 3. These are at least 4 then. And this, yeah, as I said, this guy is acting freely and linearly. Effectively, it's only acting on the odd spheres on some level. I mean, it can only fix points in even spheres. And these are the bounds you get on the dimension of this product of spheres. So, you know, as I was saying, you know, what Wiemuller did was he just did it for K is equal to, well, he did it for K equal to N, and well, K equal to N/2 when N is even. So we extended this, and then, yeah, what did I want to also comment here? Also wanted to comment that that this classification that you get, so for K equal to 2n/3, so approximately 2/3 the dimension. The statement here, well, I'm going to say is the same. I have to say what I mean, but is the same as the maximal symmetry rank conjecture for non-negatively curved manifolds. So what do I mean by the same? I mean that if the maximal symmetry rank conjecture conjectures that if I have a torus action, skip the isotropy-maximally. So if I have an isometric effective torus action on a manifold that's closed, simply connected, and non-negatively curved, then, well, this you get for free on some level, but then the conjecture is that the rank has to be less than or equal to approximately 2/3 of the dimension. And in the case of equality, so here it would not be any n, or any k in this range. It's just for, well, it's for n and k equal to 2/3 of n, you get exactly this statement. So you would be, yeah, that's still valid. So the conjecture has been verified. So in dimensions less than or equal to 9. That's work of, let me keep it there. This is by, well, a few people, I suppose. For 4 less than or equal to n less than or equal to 6, the work is by myself and Fernando Galás Garcia, as well as Fernando Galás Garcia, I should mention his last name every time, and Martin Karen. And in dimensions 7 through 9, it's due to myself and Christine Escher. So an obvious next step on some level is, what about almost isotropy-maximal? Although, yeah. So I should say what they are. So I have that written down already. So an action, a torus action on a manifold, it's hopefully pretty obvious at this point where we're going, where I'm going with this. So we say it's almost isotropy-maximal if you've got a point where now the rank of the smallest orbit potentially. So, and you, at least that you have some point whose orbit has isotropy subgroup with rank n minus k minus 1. So this is rank equal to the cohomogeneity of the action minus 1. And if this turns out to be the smallest possible orbit, then we're going to say that the action is strictly almost isotropy-maximal. So let me leave that there. So a couple of comments, I'll repeat what I said. So in this case, I mean, this is for me the easiest way to remember it on some level. TKX, so the rank of this guy is equal to n minus k minus 1. And it's worth noting that the smallest orbit, if this is strictly, and I'm going to write aim now for almost isotropy-maximal. So the smallest orbit, if it's strictly almost isotropy-maximal, will be of odd codimension. So that tells you then that the corresponding fixed point set of the isotropy group at that point will properly contain the orbit of that point. So that means that I'm using the same x as mentioned in the definition. So tk of x is contained in mt n minus k minus 1. And it's usually just of codimension. Well, it should be of exactly of codimension 1 in this case. Okay, another remark, going back to positive sectional curvature. You have no strictly isotropy, almost isotropy-maximal torus actions. This is by Berger and Sugahara again. So the case for positive curvature is really rigid. And in fact, what this tells you is that for sec positive, so for positive sectional curvature, there is no relationship between the almost maximal symmetry rank and almost isotropy-maximal actions. So yeah, so almost maximal symmetry rank at that point actually corresponds to And then we're getting too many letters here. This corresponds to almost isotropy-maximal. So you take the cohomogeneity and subtract 2, and that should be the smallest possible orbit. Okay, so at this point, there's no relationship between almost maximal symmetry rank and almost isotropy-maximal, but we're just looking at positive sectional curvature with these really strong theorems of Berger and Sugihara present. We don't have those in non-negative curvature, so it's a good time to ask, is there actually a relationship between the almost maximal symmetry rank conjecture for non-negative sectional curvature and for manifolds admitting an almost isotropy-maximal torus action? So for this class of manifolds that is closed, simply connected, and non-negatively curved. And the answer here is yes and no. I guess as with all good questions, you can't always answer them just one way. So what is the conjecture for almost maximal symmetry rank for non-negative sectional curvature states? So based on the conjecture for maximal symmetry rank, this one's going to state that the rank should be less than or equal to roughly 2/3 the dimension minus 1. And it has been verified that that indeed is the maximal or almost maximal symmetry rank, I guess, that in dimensions less than or equal to 6. That's work in dimension 4 of a lot of people. So you start off with Sheng and Kleiner. Well, actually, I'm talking about non-negative curvature. So actually, it's just Kleiner. So in his thesis, and concurrently myself and De Yang, as well as Fernando Galas Garcia and Galas Garcia and Karen, and finally Grove and Walking. Okay, so in dimension 5, though, it's work of myself and Fernando Galas Garcia. He's getting his name mentioned a lot. Hopefully he's happy. In dimension 6, Escher and myself. That should be an end. Okay, so just want to point out here, though, that almost isotropy-maximal is the same as almost maximal symmetry rank in dimension 4, but this is no longer true once you get to dimension 5. So, the pen's not working. Here we go. In dimensions greater than or equal to 5, almost isotropy-maximal is contained in but not equal to AMSR. So almost maximal symmetry rank. For example, you can just look at a T2 action would be almost isotropy. Well, a T2 action, sorry, is almost maximal symmetry rank, and there are 2 T2 actions on 5 manifolds with 1 circle acting freely. So those are almost maximal symmetry rank, but they are not almost isotropy-maximal because you only have a circle fixing, and the cohomogeneity of this action is 3. So 3 minus 1 is 2. You need both circles fixing for it to be almost isotropy-maximal. So part of the point here is to just say that, while almost isotropy-maximal and almost maximal symmetry rank are not going to be the same thing, at least understanding the almost isotropy-maximal case should help us in understanding the larger almost maximal symmetry rank classification. So one more comment, I guess, before I get to the main theorem. So I just want to note that as well. So, I said we know what happens for, and well, not really. This is unlike it. I guess I want to say that it turns out that almost isotropy-maximal and isotropy-maximal are actually the same when for sec non-negative and simply connected and closed. That's when K is spot on 2n/3. So and what follows, we generalize work of Escher and myself for isotropy-maximal torus actions in the theorem below. So, don't need to go that far. So what does this say? This maybe, yeah, so this is due to Jiting Dong, our joint PhD student, Christine Escher and myself. And what we're saying here now is that if we've got a TK action on, so a torus action on a closed, simply connected, non-negatively curved manifold, and it's isometric, effective, and strictly almost isotropy-maximal, then we can actually extend the TK isometric action to a smooth. So we lose isometry when we add in, but for our purposes, it's actually, it turns out it's enough. We extend it to a smooth TK plus 1 action, and then we get the following bounds. So you'll note that actually when n is even, so before the bound was n plus 1 over 2, less than or equal to k, less than or equal to 2n over 3. So at this point, you can see that, well, if n is even, those two are equal, but it is possible for even dimensions to have almost isotropy-maximal that are not, almost isotropy-maximal that are not isotropy-maximal for that dimension. But for the odd, you have to go one down, basically. So we get these bounds. So since we're talking about it being strictly almost isotropy-maximal, we lose the 2n over 3. And then it turns out that once again, the manifold then is equivariantly diffeomorphic to a quotient of a product of spheres. So again, this was a product of even and odd dimensional spheres of dimensions bigger than or equal to 3, modulo a free linear torus action, and they're equivariantly diffeomorphic with a linear now TK plus 1 action. And now we lose a little bit on the dimension. So, now the maximum dimension of this manifold, this product of spheres, is going to be 3n minus 3k minus 3. Okay, so I was gonna, well, I guess what I should say, maybe a quick summary of this is that it's just to say that if we have a TK action on Mn and it's strictly almost isotropy-maximal, this corresponds to having a TK plus 1 action on the same dimension that's isotropy-maximal. So I wanted to spend the rest of the time available sketching the proof. So the first thing I want to start with, I guess I should stop and say, are there any questions at this point? So it's a problem with Zoom. I got to take some water too at this point. Okay, so no one's saying anything. I'm just gonna keep moving. So how do we prove this? I'm kind of like synthesized it into 3 steps. So the first thing I want to recall, though, is just in case you're not familiar with the notation, is that because this is an important concept. So we talk about a torus action, it'll come up. I'm not going to really go into much depth about it, but at least, so the word isn't totally unfamiliar. So we talk about a torus action on a manifold being locally standard if for every point in the manifold, you've got a neighborhood of that point that looks like this. So it looks like an orbit. So this is where TR is an orbit. That is, R is the dimension of the, or the rank of the action minus the dimension of the isotropy subgroup, or rank of the isotropy subgroup, meaning the same thing. So it's going to look basically like an orbit across an even dimensional space cross, well, like a C to the sum K, right? C to the L, I guess I should say, cross Rm. And W here is going to be a faithful isotropy representation. So isotropy at that point representation of dimension 2 times, this is K minus R. So that is the dimension of this guy. So the dimension of W, I'm not saying it well. The dimension of W is then 2 times the dimension of this guy, the isotropy. And the following actions are trivial on here. So the TK, all of TK acts on Rm trivially. The TR component of TK, when you split off the isotropy subgroup, is gonna act trivially on W, and the isotropy subgroup obviously acts trivially on the orbit itself. Okay, so the first step in the proof is to, why I'm saying locally standard is we want to generalize the following proposition from the work of Escher and myself. So in this work, this proposition, what we show is that if we've got an isometric effective isotropy-maximal action on a closed, simply connected, non-negatively curved manifold, then the torus action will be locally standard, and the quotient space of the manifold and all of its faces are going to be diffeomorphic to disks after smoothing corners. So I want to make a couple remarks about why this is important. So first of all, well, this is just kind of history. This that I'm calling prop A, this generalizes. Well, I'm going to rate lemma 6.3, which is kind of crazy because maybe you guys haven't read this, Wiener's classification of torus manifolds. It's a really long lemma and it's crucial in the proof. So this was for isotropy-maximal Tn actions on M2n. This is where M2n is closed, again, simply connected and non-negatively curved. So it generalizes this crucial lemma for Wiener's classification, and it turns out that this was also a crucial proposition for us. So this was crucial for Escher and myself. There are two S's, sets of S's, I guess, here. So this was crucial in the proof of the isotropy-maximal equivariant diffeomorphism classification. Basically, that, as the really, well, this is important, but maybe more important than that is showing that that isotropy-maximal in this context gives you locally standard. And once you have locally standard, then you can apply a cross-sectioning theorem that we had that was essential to getting the equivariant diffeomorphism. And the cross-sectioning theorem requires that the action be locally standard. You don't get it otherwise. Not, or at least not that we know how to do, I should say. So what happens though if I'm looking at almost isotropy-maximal? So we actually don't get a full generalization. And I should say we never expected to on some level. So we don't expect to either. And that's because I'm going to give a couple of examples here. So if I look at a T1 action on S3, for this to be isotropy-maximal, it needs to be, it will fix a circle, a codimension 2 submanifold. In particular, we know that, so it fixes a circle, it's codimension 2, that will be the boundary of the quotient space. So S3 mod T1 is going to be a 2 disk, and we have F equal to fix of S1 is a circle. I made it that way. So what happens, what does my quotient space look like? Let's see if I can do this actually. So this will be my quotient space. And in this particular case, this is my F. So F here is, fixed by, this is fixed by a circle. This has trivial isotropy. And that's, you can see here that this F, I mean, so what did the proposition A say? It said that the quotient space, M mod T, and all of its faces, so the F in this case is a codimension 1 face, are diffeomorphic to disks. So obviously a circle and a disk, they're not diffeomorphic. So we don't get it here. And just, by way of contrast, if it is isotropy-maximal, so if you look at, say, a T2 action on M4, again, your orbit space is going to be a disk. But in this case, it turns out that, let me see if I can do this. You get a couple of possibilities here. I love the shape tool. And what else do I get? These are the only 4 possibilities I get with non-negative curvature. But in these cases, these are points that are fixed by the T2. So by the whole action, again, same over here, all these points. But all the codimension 1 faces are intervals, which are disks. So, I mean, this just affirming what the proposition says. And you can take a point to be a disk too. So all the lower dimensional faces, not only is the space itself, each one of these spaces is a disk, but all of its faces of any dimension are going to be disks. Okay, on the other hand, though, as I'm saying, we don't get a full generalization, but we do get enough for our purposes. Okay, so yeah, as in the one night, so this goes to this comment that I made a while back that when I have a strictly almost isotropy-maximal torus action, we end up having then the smallest possible orbit is of odd codimension, which means that it sits properly inside of the fixed point set corresponding to that isotropy subgroup. And as a result, just as in the isotropy-maximal case, we get a circle sitting inside of our torus that is acting fixed point homogeneously. So a fixed point homogeneous circle action corresponds to the case where you have a codimension 2 fixed point set. And then this allows us to use, so the fact that almost isotropy-maximal and isotropy-maximal both have this codimension 2 fixed point set of some circle, and then that contains the smallest orbit as well, allows us to use this theorem of Spindler, which says that if we've got a group that acts isometrically and fixed point homogeneously, so that's the correspondence here on the manifold. If it's closed and non-negatively curved, then if you pick that a component of maximal dimension in the fixed point set of the whole group acting, then you get that the manifold decomposes as a union of disk bundles. And this is super important. This is like why all of this stuff works on some level. So this is where, this is F is this largest fixed point set component, and N is going to be a closed G invariant submanifold. And all of the singularities of the G action are contained in F and N. So that means that everything outside of F and N, those are principal orbits, which gives you a lot of, it's a really strong result. Okay, so the generalization, I'm not going to write down the generalization of prop A, but I'm going to kind of just summarize it. It gives us the following. So first, that the TK action is locally standard, not on the whole manifold like we had before, but it is locally standard on F in this decomposition, on the entire disk bundle around F, and on N. And we also get that that the quotient space M mod T, the full quotient space, is diffeomorphic to a disk. And all we know at this point is that the facets, which are the codimension 1 faces, these are diffeomorphic. Again, this is all after smoothing corners too. So they're diffeomorphic to either disks of 1 dimension lower or a product of a disk and a circle. So again, after smoothing the corners. Okay, I wanted to make, well, it's getting on. So I guess a couple of quick remarks. the proof is by induction. On the cohomogeneity. Of the action, and that, well, the other quick remark is just that we don't know, you know, all the stuff we've been saying is for closed simply connected manifolds. In order to apply the induction hypothesis, it would be great if F and N were always simply connected, but they aren't. But what we do know is that both of them have cyclic fundamental group. And so sometimes, well, so when it's not trivial, you have to do it kind of a dance with the universal cover and lifting the action and using the splitting theorem of Cheever-Grammel and yeah, and then in order to apply the induction hypothesis. Okay, so the second step is this extension theorem. So yeah, since I'm just going to mention this, and that, so this extension theorem says that if I've got a closed, simply connected, non-negatively curved manifold emitting an isometric effective and strictly almost isotropy-maximal torus action, then that torus action extends to a smooth TK plus 1 action. And it turns out that this TK plus 1 action is going to be locally standard and an isotropy-maximal. So, yeah, and that's great for us at this point. So again, I guess just to point out, the proof is again by induction on the cohomogeneity of the action. And then I'm moving on to the third step, which is, you know, how do we prove this theorem? So I think I can say that in the last 4 minutes. So first thing to note is that we've got, so I've got, what was my setup? It was I have TK on MN and it's strictly almost isotropy-maximal. You can show that there is a 2K minus N, let me get this right, plus 2 torus sitting inside now of this extended TK plus 1. So I'm already, actually, let me just move this down. So I should say use extension theorem. And you've got this TK plus 1 on MN, and it is locally standard and isotropy-maximal. Okay, so this ends up giving us that we have this relatively large torus sitting in the larger torus here, acting almost freely. On the manifold. And then that gives me that if I look at the quotient of the manifold by this almost freely acting torus, I get an x to the 2n minus 2k minus 2, and that's this mn modulo this torus. Okay, and this actually, this space admits a t n minus k minus 1. So if you take, yeah, you just subtract this rank from k, and that's what you end up with. So you got a tk n minus k minus 1 action on x2n minus 2k minus 2 that is isotropy-maximal, and that implies that x2n minus 2k minus 2 is a torus orbifold or a torus manifold if the action is free. Okay, so then this is great for us because there's been a lot of work on torus orbifolds and torus manifolds. Moreover, we know the following. So this is all just, you know, we have a smooth action right now, TK plus 1. But if we go back to the case where we said, you know, this part of the action, this is isometric, right? So what we know is that for a strictly almost isotropy-maximal torus action on a manifold, that if the manifold is non-negatively curved, simply connected and closed, that the manifold then must be rationally elliptic. So that's something that Christine and Escher and I showed, generalizing a similar result. It's also true for isotropy-maximal actions. That part's due to Galás-Garcia, Karen, Radetzky, and Wiemeller. Okay, so what I was saying is that M is rationally elliptic. And then the nice thing is that then that means that because quotients by almost free actions on rationally elliptic manifolds are rationally elliptic, that means that this x2n minus 2k minus 2 is also rationally elliptic. And then we are almost at the end here. So in part of, so Galás-Garcia, Karen, Radetzky, and Wiemeller looked at torus orbifolds of non-negative sectional curvature and, well, non-negative curvature, I should say, actually. So they were looking at, well, they were looking at torus orbifolds, I should just say. And in the proof of one of their results, they show, so let me write their names just because I've been writing everybody else. So let me do it this way. So using an argument in the proof of a result from, this is Galás-Garcia, Karen, Radetzky, and Wiemeller. This, now that this torus orbifold is rationally elliptic, this now tells us that if we take the full quotient m mod t, which is then x2n minus 2k minus 2 mod this t n minus k minus 1, if I name that p n, I'm running out of space. That's p n minus k minus 1. This guy has a phase poset, or it has a phase poset, I should say, that is combinatorially equivalent to the following product. So it's a product of, I will say what I mean by these. So these are ni-dimensional simplices. So that's an n sub I simplex. And this is an n sub I lunar suspension. And that's a lunar suspension of ni minus 1 simplex. Okay, so this has the phase poset, it has the phase poset of this quotient space. So the phase poset of this guy is combinatorial equivalent to this product. And then there's a result of Davis. So that then tells us that m mod t is actually equal to this product. And then we can use all the machinery that Christine Escher and I developed in the classification of, in this equivariant diffeomorphic classification of TK plus 1 isotropy-maximal actions on closed, simply connected, non-negatively curved manifolds. We can apply all of it to this situation, and then we get the result. So yeah, that's it. Then use machinery from proof of the IM equivariant diffeomorphic classification. I can't spell. And that's it. So, and I'm over time, so I'll apologize for that. Sorry. But yeah, thank you for listening. That's it.
Thank you. Thank you for a very nice talk.
Thanks.
Are there questions? Well, if there's no questions, thank you again.
Thanks. Thanks.